In this video, I'll show you how to solve the ALEKS problem called percent yield of chemical reactions. This problem is really tedious, so it's one that you want to really take your time on, make sure you're doing everything correctly so you don't have to do it too many times. The first thing that we need to do is use all the words in this problem to write a balanced chemical equation. This problem is telling us that we have liquid hexane, which is CH3 parentheses CH2 parentheses 4 CH3, and it's reacting with oxygen gas to produce carbon dioxide, CO2, and water, H2O. This one looks like it's just going to be pretty tedious to balance, so I'm just going to start by writing up all of my atoms. I'm not even going to try to balance it, just by looking at it. And I'm going to count up how many carbon atoms I have. I have 1 times 4, so that's 4. 1 plus 4 plus 1 is 6 carbon atoms. And then for my hydrogens, I have 3 plus 2 times 4 is 8, plus another 3. 3 plus 8 plus 3 is 14. And I have 2 oxygens. And on the right-hand side, I have 1 carbon, I have 2 hydrogens, and I have 3 oxygens. I'm going to begin by balancing the carbons. I have 6 on the left. To give me 6 on the right-hand side, I'm going to put a 6 in front of that CO2. That's going to change my carbon atoms to 6. It's also going to change my oxygen atoms. I now have 6 times 2 is 12, plus 1 is 13. Hydrogens are next. I have 14 on the left. I need 14 on the right. I'm going to put a 7 in front of the H2O. That's going to change my hydrogen atoms. 7 times 2 is 14. It also changes my oxygen atoms. So now I have 6 times 2 is 12, plus another 7, that's 19. Now I'm ready to balance the oxygens, and I'm in this situation. We call this interfering coefficients. I need 19 oxygen atoms on the left-hand side, but the oxygen atoms only come in multiples of 2, so it's impossible for me to put a coefficient here and end up with 19. So when I am in a situation like this, what we do is stop, pause, and double everything that we already have. So I'm going to double all of these stoichiometric coefficients, multiply everything by 2. So instead of 6 here, I have 12. Instead of 7, I have 14. And then also, we have to double all of these. So instead of 6, I have 12. Instead of 14, I have 28. Instead of 2, I have 4. This is 12, this is 28, and 19 times 2 is 38. So this, by doubling everything, that takes that odd number and it turns it into an even number. Now I need 38 oxygens on the left instead of some weird number. So the question becomes, what times 2 equals 38? It's just 19. 19O2 is going to give me 38 oxygens on the left. So once I get the equation balanced, what I'm going to do is erase this like bookkeeping that I did here to just give myself a little bit more room, and now I'm ready to work on the problem. Like, we haven't even actually started the problem yet. The problem is telling us that we have made 20.1 grams of water. Oh my gosh, 20.1 grams of water. And it came from the reaction of 35.3 grams of hexane and 73.5 grams of oxygen. And it's asking us to calculate the percent yield. The percent yield is calculated from the equation. Take the actual yield, having a hard time writing up there. I'm going to write. So we're going to take the actual yield, divide it by the theoretical yield, and then multiply that number by 100. The actual yield is the number that is actually produced. So the problem tells us that we produced 20.1 grams of water. That means that it is our actual yield. That's our actual yield. The theoretical yield is a number that you have to calculate using stoichiometry. And in this situation, we have to calculate that theoretical yield from the 35.3 grams of the liquid hexane, and we also have to calculate the theoretical yield from the 73.5 grams of O2. So since they've given us starting amounts for both of the reactants, we have to calculate that theoretical yield 2 times. One time starting from the 35.3 grams of hexane, CH3, CH2, 4CH3, and a second time starting from the 73.5 grams of O2. So like I said, this problem is super tedious. We're going to do 2 calculations, and what we're doing here is calculating how much water, like what is the theoretical amount of water that we can produce from the hexane. We're also going to do that same calculation for the O2. What's the amount of H2O that we could make from the O2? So the first thing that we have to do is get rid of these units of grams, CH3, CH2, 4CH3, and we want to convert into units of moles, CH3, CH2, 4CH3. Adding up these molecular weights can be pretty tedious, so it's handy to go to the internet and just look them up. What is the molar mass of hexane? 86.18 grams per mole. You could have also typed in the formula instead of typing in the name. Either one of those would have worked just fine. 86.18 grams per mole. So that's just going to save you a little bit of time looking up those molecular weights instead of adding them up yourself. And then the next thing that we want to do is a mole to mole conversion. So we want to get rid of these units of moles of CH3. Oh my gosh, this is such a long formula. CH2, 4CH3. We want to cancel that unit out. We're trying to figure out water. So we want to convert into moles of H2O. So what we need to do here is use the stoichiometric coefficients from the balanced equation. For water, the stoichiometric coefficient is 14, and for hexane, the stoichiometric coefficient is 2. I hope that that's a 14. My handwriting's a little bit messy there. I think that that's a 4. I'm going to go with it's a 4, but maybe that's a sloppy 9. Maybe this should be a 9. So we'll cancel those units out. And then the last thing that we need to do is convert from moles of H2O into grams of H2O using the molecular weight, 18 grams per mole, 1 + 1 + 16 for H2O. And we'll crunch the numbers on this. 35.3 divided by 86.18 times 14 divided by 2 times 18, this gives me 51.61 grams of H2O. This is the amount of water that we can make if we start with 35.3 grams of hexane. Like I said, we have to repeat this calculation for the oxygen. So as I said, this is a tedious problem. It's one that you definitely want to take your time on because there's a lot of ways, a lot of places where you could mess this problem up. So we're going to do all of this all over again, this time starting with the 73.5 grams of O2. First thing that we need to do is convert out of grams of O2 into moles of O2, and we do that using the molecular weight of O2, that's 32 grams per mole. The next thing that we need to do is convert out of moles of O2 into moles of H2O. So I'm really just following the pattern that we took up here, but I'm using O2 in place of the hexane. Stoichiometric coefficients go into this conversion factor. So for H2O, I'm sticking with 14. It might be 19. My handwriting is kind of messy right now. 19 is the stoichiometric coefficient for the O2. And then the last step, we're going to convert. Here's our last step. We're going to convert from moles of O2 into moles of H2O into grams of H2O. 1 mole of H2O is 18 grams. Double check to make sure that the units will cancel themselves out correctly and do the math. 73.5 divided by 32 times 14 divided by 19 times 18. this gives me 30.46 grams of H2O. So what we've done here is calculated 2 masses of H2O. We've calculated 2 theoretical masses of H2O. And of course, they both can't be correct because they're not the same number. One of them is correct and one of them is a lie. When you're looking at these two numbers, and this is a very common mistake that students make because students want to go with the big number, it makes sense. The correct number is always going to be the small one. The big number is always a lie. No matter how much hexane we have, we only have enough oxygen to make 30 grams of water, and once we've made 30 grams of water, the whole reaction is going to stop. So even though we have enough hexane to make 51 grams of water, we're never going to be able to make that much because we are limited in the production of water by the small amount of O2 that we have. So this right here is our theoretical yield. And we're almost done with the problem. We are now ready to calculate the percent yield. The percent yield is the actual divided by the theoretical multiplied by 100. And as I said, the actual yield is a number that's given to you by the problem. So the 20.1 grams, that's the actual yield. You always have to be told what the actual yield is. There's no way to calculate it. The theoretical yield that we calculated is the 30.46 grams, the smaller of those two numbers. Multiply it by 100 to make it a percent. 20.1 divided by 30.46 multiply by 100 gives me 65.988, and I want this to 3 sig figs, which looks like it's going to be 66.0%.